Today we are going to discuss about the doped fiber amplifier. As I mentioned earlier, there are different types of optical amplifiers, semiconductor optical amplifiers, doped fiber amplifiers, and Raman amplifiers. Here, doped fiber amplifier or DFAs are optical power amplifiers that use a doped optical fiber as a given medium to amplify the optical signal. So, in case of in the previous session, we were discussed in detail about the general operation or the general principle behind the optical amplifier. There is an active medium that is the important part of the optical amplifier. Here, in this case, DFA, the doped fiber amplifiers, the one thing is important thing is that the active medium of the optical amplifier that is made up of doped optical fiber. Okay, that is a given medium to amplify the optical signal. So they are related to fiber lasers. The signal to be amplified and the pump laser are multiplexed into the doped fibers. Here, the signals to be amplified is coupled to the fiber amplifier couplers through the active medium. And in this active medium, from the pump laser, so from the pump source, the signal is multiplexed with the signal to be amplified, and we get the amplified output as optical signal in the output of doped fiber amplifier. The most common example is erbium doped fiber amplifier. That's why we call as EDFA, erbium doped fiber amplifier. So the signal is amplified through the interaction with the doping ions. Here, EDFA, the erbium ions are used for the doping. The core of silica fiber is doped with trivalent erbium ions that can be efficiently pumped with the laser at a wavelength of 980 nanometer or 1480 nanometer and exhibits a gain in 1550 nanometer region. Okay. Then now next we are going to the basics of the EDFA. So the basics of Erbium doped fiber amplifiers that it is used to boost the intensity of the optical signals. Basically, it is used to the boost the intensity of the optical signals, and it has a fiber whose core is heavily doped with erbium ions. That's why it is named as erbium doped fiber amplifiers. So it works based on the concept of the stimulated emission, as I mentioned earlier. So all of you are familiar with the concept of stimulated emission and the population inversions in the case of laser working principle also. So EDFA works based on the concept of stimulated emission, and it operates in the C band. C band, that means 1530 nanometer to 1560 nanometer. That is C band, and it operates in also C band and also in the L band. So I think you are familiar with the different bands, C band, L band, etc. So the L band, that means 1570 nanometer to 1610 nanometer. Okay. So why erbium? So there are so many atoms or material available for doping. Then why we use erbium here? So because we are using the erbium here, and it's named as erbium doped fiber. So what is the reason behind that? Erbium ion Er 3 plus have the quantum levels that allows them to be stimulated to emit in 1540 nanometer band, which has the lowest power loss with the silica based fiber. That's why we use the erbium ion. So erbium quantum levels also allow it to be excited by a signal at either 980 nanometer or 1480 nanometer, which has highest loss in silica based fiber. These are the two reasons behind erbium. So why erbium is used here? And working of EDFA, we can explain the working of the EDFA. Here, the laser pump, as I mentioned earlier, as we discussed in the previous session, there is important two parts of the optical amplifier is a pump source and active medium. So the laser pump energy at 980 nanometer or 1480 nanometer meter. In this wavelength, the laser pump energy, the two active medium, high energy and weak signal, high energy and weak signal mixed by a wavelength selective coupler. Here, the weak signal, that the signal to be amplified. So that signal mixed with the high energy signal from the laser pump source. Okay. ER3 plus ion in the active medium. So the active medium is doped with the ER3 plus ion. These ER3 plus ion absorbs the energy by laser pumping and gets excited to the higher level. So this excitation, so by accepting the energy from the laser pumping, the ER3 plus ions can absorb the energy and which can excite it to the higher level. So this excitation that leads to the population inversion and also that the stimulated absorption and emission. So these stimulated absorption and emission that will amplify the weak signal. That is the basic principle or behind the working of the EDFA. Here we can see the band diagram, band energy diagram or energy level diagram of a diagram with various transition across of ER3 plus ion in silica. Okay. Here you can see that various energy levels and there is a metal stable state and pump transition, etc. So what is happening here? We can explain these things. That is, initially all the carriers are in the ground state. So initially all the carriers in the ground state. Now pump energy of 980 nanometer are absorbed by carriers and they excited to the extreme high energy level called pump band. You can see in the figure. So initially all the carriers are at low level. From that, by absorbing the 980 nanometer of photon that from the pump laser pump source and the pump transition occurs, that carriers excited to the pump band we can see in the figure as numbered as 1 here. And by non-radiative decay, energized electrons are in the pump band or move towards the metastable state. So immediately after these carriers excited to the pump band by accepting, by absorbing the 980 nanometer energy, and it is in the position of pump band, that is one. From that pump band, it can move to the metastable band by a fast non-radiative decay. Yeah. So by non-radiative decay, energized electrons are in the pump and are move towards to metastable state. Okay. This non-radiative decay is due to the thermal and mechanical vibrations of the laser ion. Okay. And in the third stage, the signal absorption takes place and the laser energy pumping is of 1480 nanometer. In the metastable state, I think you're familiar with the laser working principle. This metastable level, that is the main things for the population inversion. And that's why here we get the population inversion in the metastable state. And the accumulation of the accumulation of carriers or the increasing of the number of carriers in the metastable state, that may create a population inversion, that is more number of carriers at the metastable state. From the metastable state, there is actually the stimulated emission happening there. Okay, from that metastable state, so by the population inversion, the which leads to the stimulated emission and which emits the laser or optical signal of the frequencies. Okay. Then the carriers move to the metastable state from that. Okay. Then again by non-radiative decay, and as I mentioned here, carriers fall to the lower energy band of the metastable state, and few of the carriers undergo the spontaneous emission of 1550 nanometer wavelength, and weak signals will provide stimulated absorption at the 1550 nanometer. Meanwhile, so many charge carriers in metastable state with a little force will undergo the stimulated emission. This will take place due to large amount of charge carriers in the metastable state. So the weak signals undergo amplification due to the stimulated emission of charge carriers at 1550 nanometer. This is actually the working of the EDFA Erbium top amplifier. That's why each signal amplified by using these erbium ions. Okay. These are the architecture of the EDFA as shown here, the different type of architecture. So in this the first figure, you can see that the signal input and laser pumps are in the same direction. That's why it's called as co-directional EDFA. There are the different types of EDFA or the architecture of EDFA. Here the co-directional means signal input and the laser pumps are in the same direction. So in this figure, you can see that that's called co-directional erbium ducted fiber amplifier EDFA. And the counter directional EDFA, here the signal input and the laser pumping are opposite to each other. Okay. In this figure, you can see that the signal input and the pump laser is in the opposite direction. In this case, that EDFA is called as counter directional EDFA. Okay. Then dual pumping EDFA is another type of EDFA, another type of architecture. That is, the laser pumping is in two directions, that opposite to the output signal direction. That is, the two directional laser pumping is there. Pump laser, one direction you can see here, the two direction, and the input signal laser pumping is in two direction and opposite to the output signal direction. Okay. These are the different architecture of the EDFA or the different types of DFA. And applications of EDFA, the applications of EDFA that may include high capacity and high speed optical system. In the case, in the case of high capacity and high speed optical system, we can use the EDFA, Erbium dubbed fiber amplifiers. And for the long hand optical communication, we can use it. And optical fiber subscriber networks, WDM systems. The WDM systems we will discuss in the next module in detail. There is wavelength division multiplexing systems and the community antenna television system, that's CATV. These are the applications of EDFA. And the advantages of EDFA is that the commercially available in C and L band. That is one of the advantage of CDFA. And the insensitivity to polarization state. There is an important advantage. So these EDFA are insensitive to the different polarization state, and that provide high gain and also better amplification and no distortion at high bit rates and immunity to crosstalk and do not require high speed electronics and independent of bit rate. These are the advantages of EDFA. And there are some disadvantages of EDFA. That is, pump laser is necessary in case of EDFA. This is one of the disadvantages. And need to use gain equalizer for multi-stage amplification. Okay, also one of the disadvantages. And it is difficult to integrate with the other components. That is also the disadvantages of EDFA.